Hello everyone, I am Gianluca Aguzzi, a PhD student from University of Bologna, and today I'm here to present my paper entitled Addressing Collective Computation Efficiency Towards a Platform-Level Reinforcement Learning Approach. In my research, I'm mainly interested in collective adaptive systems that are the one composed of hundreds, thousands of agents that interact with each other in order to reach global goal. In order to do that, they expose collective behavior. Consider, for instance, the case of swarm robotics. If the goal is to reach a destination, the agent typically show a flocking behavior as bees or other social insects in order to avoid with each other. In that case, we have a lot of challenges because we have to deal with distribution due to the fact that does not exist a global authority that can coordinate the whole system. Then there are a lot of uncertainty, both at the environment level, that typically can be not stationary, and both at the system level, so we can have failure, or the agent can join to the system, and so on and so forth. And moreover, we have the problem of global to local mapping. Indeed, in this kind of system, we typically have a global specification, and we want to break it in local behavior, but it's typically very complicated. Now, before to introduce the problem of collective efficiency, let me introduce you a motivating example. And in this case, it is the distributed sensing in the case of collective adaptive system. This is a general framework that can be used in several use cases. For instance, consider the case of monitoring with fire in forest. We have a lot of drones that check if there are fire. In the case of fire, they have to send alarm or perform, for instance, local action. But another use case could be the one in cloud engineering, that we want to verify if there are zones that are overcrowded, and in that case, sending alarm or steer the crowd to another place, and so on and so forth. There are also other examples, for instance, the one in agriculture monitoring, also avalanche monitoring. How can we implement that kind of behavior in this system? We can use some of collective patterns that are really well known in the CAS scenario, so in the collective adaptive system. One of the most important is the gradient cast, that have the goal to send information from sinks node to other node, and during this process of propagation they accumulate information. This block can be used for indeed share decision from sink node. Another block, it could be the data collection, that is the block that is inverse of gradient cast, and it is used to collect information in the sinks node. This can be used to have a global view of a certain zone of the system. And finally, another very important block is sparse choice, that is used to perform a distributed linear election, and so to create sync node at runtime. This block in collective adaptive system can be programmed in a way that are self-organized and self-stabilizing. That means that even if there are perturbations, the system lead to another stable configuration autonomously. Okay, now come back to the specification of distributed sensing. We can express this behavior using that block. In particular, first of all, we have to create the sinks node that can be made with the leader election. The green is used to tell how much the area should be big. Then, using that center, we can diffuse the information in which we define how to send the data in the sinks node, and this can be used with diffuse, that is the gradient cast. Then we have to have a vision of the zone that are near to the sync node, so we use collect to get the perception of the node, and in some way having this global view from the sync node. After retrieving this information, the sync node can make decision and share this decision with the system. Okay, this is the general specification. Now we have to speak about how we can execute the global definition. This can be executed with a simple behavior, that is the typical sense compute act. In particular, each agent sends the information from environment and get the information from neighbor that can be used then to compute the maze logic. This computation can eventually lead to local actuation or also in broadcast message to the other nodes. and then this behavior should be scheduled. And the scheduling can be defined in many ways. For instance, can be method based, so the execution is triggered when agent receive message, or can be sensor based, so the execution is triggered when some environment perception change, or time based, that is the simple one, and is the one that defines that the agent should compute with a certain rate. And finally, there is the general one, that is event based, that is could be a combination of the previous one. Okay, now let me speak about collective computation efficiency. The idea is that we have a global specification, as the one that I show you with distributed sexing and act, and we have several execution strategies. The point is that an execution strategy can influence the global behavior. Why? Because if we choose an execution strategy that compute a lot of time, it eventually lead the system to converge a stable configuration faster. Now, what are our goals in choosing this execution strategy? We can choose an execution strategy that reduces the power consumption, and in this case we are focused on green computing aspect, but at the same time we can also be interested in reduce the convergence time. Typically it's a multi-objective nature, because if we reduce the power consumption, we can increment the convergence time and vice versa. In general, there are several approaches to choosing that scheduler. One could be rule-based. In this case, there are several rules that can be triggered different scheduling policy. Another way could be using reinforcement learning to understand how the agent and when agents should compute. And this is the direction that we follow in this paper. But first, let me make some example. In this case, consider this video that shows the distributed sexing and active in a simple environment. In particular, here the node track this phenomena that is a Gaussian distribution. The inner circle divides the computation, how much the power is consumed. The outer circle is the perception that the node made, and the outer circle, the gray one, divides if the nodes are leader or not. As you can see, in this case, the nodes are super fast to converge a stable configuration, and then they are able to follow the phenomenal movement. But if we try to use another strategy that leads a low consumption, the convergence time is delayed, and so the system cannot be able to track well the phenomenon, as you can see in the video. What we want to do is to have a kind of adaptive solution. So the system at the beginning compute fast, then reduce the computation because the phenomenon is not changing, and then when the phenomena start to move, the nodes start to compute again. Okay, so now we can discuss about the contribution of our paper. In particular, in the article, we show how to reduce the power consumption of some of the self-organizing building blocks, such as grading cast and data collection. As a reference learning technique, we use a variation of Q-learning, that is a value-based reinforcement learning approach. As a reference framework for devising a self-stabilizing building block, we use aggregate computing, that is a top-down, global-to-local functional programming approach that is used for expressing self-organizing collective behavior. We made this choice because aggregate computing is a good match for expressing our solution, and moreover it has already implemented a lot of the building blocks, such as the grading cluster data collection, and it could also have this integration could also have a high potential impact in the aggregate computing research. The benefit of this integration are that reinforcement learning is applied at the middleware level, so it does not change the semantic of aggregate computing, and moreover we separe the functional aspect of the program, that is indeed at the high-level specification, from non-functional aspect that could be the aspect of energy consumption, the convergence time, and so on and so forth. The idea is quite simple. We use time-based scheduler, and we wanna learn when to reduce the round frequency, maintaining a good reactivity with respect to the environmental changes. The learning settings are the ones that are similar in the swarm-like system. So it is a multi-agent setting, and we have an homogeneous behavior, since in that case the complexity of the system emerges from interaction, and indeed this is a typical choice in swarm-like systems. The training approach is a centralized training and decentralized execution. The idea is that we use global information during learning, and we update the Q-table globally during the simulation, but then this Q-table is distributed during runtime, and in particular the state is built only from local data or data that are get from neighborhood. In this way the learning is eased because we have a global view of the system. So in the figure we see how each episode is devised. We have a Q-table that is shared, and we have a learning process that improves the Q-table, and then we have several episodes. At the end of this episode we compute a global Q-table that is the optimal one, and we share it with the agents. Okay, so now let me speak about the state, the action, and the reward of each agent. The state is what we call a local output derivative. We maintain a window for local changes that are used to understand the variation of the output in the time. In particular, in the each element of these windows could be rising, stable, and decreasing. That is, say, if the output is rising or is stable or is decreased. The action are the next wake up time. So there are integers that express when the agent should recompute the program, and is a fixed set in this case. And the reward try to weigh the contribution of agent in a way that if the agent are in a non stable condition, so there are a lot of variation, the reward is negative. When is in a stable condition, the reward weigh the contribution based on the next wake up time. So the bigger the wake up time is, the more the reward is near to 0. In this way we have a multiple objective nature, and so we use a weight that weigh the non stability with respect to the power consumption. Okay, so now let me conclude with the simulation configuration. The idea is that we want to learn to reduce power consumption. That can be also seen as we want to maintain the same power, but we want to converge quicker. What are the blocks that we focus in this case are gradient cast and data collection, and we want to also verify if the policy that we find with the reinforcement learning could generalize in several deployments, so, such as varying the node size. In the training phase we use 100 nodes that are placed in a semi-random grid, and in simulation we put a random seed in a way that this seed influences, for instance, the variation of the environment and the variation of the scheduling, introducing a little random delay. And then the performance are verified in different conditions, such as we try to use multiple sig node, and we also introduce multiple variation. This is an illustration of how the simulation is. In particular, we have on the left side the node that is the sig node, and you see the output influence from the sig node. It is red, and then the sig nodes change at some moment in the other position. In the evaluation, we are focused on verify the performance by varying the node in the system, and also we wanted to verify how it is better with respect to unmade policies that try to reduce as much as possible their power consumption. The experiments are publicly available at these addresses, and here we have a fast overview of how the solution goes. In particular, we see that the system over the per episode reduce the error that is the measure with respect to a policy that does not change the frequency, and also we see how in the time the ticks increase due to the fact that obviously to have a good conversion time we also have to use more ticks. And here are pictorial representation of the policy that we learn. In particular, the nodes, internal node show how much the nodes compute. The blacker the node is, the less the node compute, and we see here there is a variation. A node become green, and eventually this variation will be moving all in the system, and the node start to turn off to reduce the power consumption. This policy reduce kind of 60% less with the standard solution. In this case, the standard solution is the red line, and the solution with reinforcement learning is the blue line, and the red line is the solution made handmade. As you can see, obviously the handmade solution consume less with respect to the reinforcement learning solution, but if we look in the arrow that is in the right, we see that introduce a big error that is kind of 60% with respect to the reinforcement learning that introduce at most 10% error. And moreover, we also check how the policy deal with the variation in the nodes, and in this case the error does not change in varying the nodes, that instead is changed in the case of the ad hoc solution. So concluding, the system eventually learn a policy that reduces the collective power, maintaining a good convergence time, and also the same policy work with several deployments. That is very important in the context of collective adaptive system. This is obviously a preliminary work, so we plan to use scheduling policy as an action, so we create more complicated policy, and also we plan to use deep reinforcement learning to encode more information in the local state. We wanted to explore more the multiple-objective reinforcement learning to better represent the problem. In this case, we use only a weight, but is the linearization that sometimes does not explore well the Pareto solution. And then we wanted to extend the learning to a fully online and distributed version. So thank you for your attention, and now I'm here to reply to your question.